Today we are discussing problem 39. This is under the topic of equilibrium. You can see the statement on the board where a weightless rod, weightless means compared to the other weights given in the figure, this weight of the rod AB can be, or it is given as a bar, can be the weight of AB bar can be neglected. So for our calculation purpose, we don't need to consider the weight. Only the other forces given. One end is 10 Newton weight is suspended at one end. The other end is connected to a string which is supporting a 50 Newton weight. So that 50 Newton will remain as the tension in this rope and is making 37 degree to the vertical. Now if you leave it as it is, due to the two forces as well as also some small negligible weight, this will simply fall down. So to prevent that and to keep it in equilibrium in the horizontal position shown, what is a single force that we have to apply to this? That is the question. A single force, that force, single force, we have to get the magnitude, direction and point of application. Three things we have to work out in this. So to work out the three, these three information, to get this, work out this, we first consider the equilibrium, means because as I said, due to the weight attached etc., this is likely to fall down. So there should be some vertical component of force to balance it, which is, I marked it as Y, vertically up. Then this 50 Newton will have a horizontal component which is given by 50 sine 37 degree. Due to that, this bar has a tendency to move to the right. So that should be prevented, means there should be a force X directed to the left, horizontal force, horizontal component X. So once we find X and Y, resultant of X and Y, that this being a right angle, will be our required force F. The required force F, I have marked it, and this is theta gives the direction of that. So first equilibrium equations. First vertical equilibrium. So Y is the upward force. Y must be equal to to balance it, 50 cos 37 degree down plus this 10. Cos 37 degree is 4 by 5. So we get 40 plus 10, 50 newtons. Y component is 50 newtons. Then X is, to balance this, 50 sine 37. So X is equal to 50 sine 37 degree. Sine 37 degree being 3 by 5. So you get 30 newtons. So required F, magnitude wise, required F is equal to, F equals x square plus y square square root. That is the required force, which is 50 square plus 30 square. We'll get, we will have 34,000 square root of that. So which implies F equal to 58.3 newtons. or you can say 10 root 34, which is equal to 58.3 newtons, which is the magnitude. F equals 58.3 newtons. Now the direction of that force, I will clear some part of this to get the direction of the force. To get the direction, we go by from the diagram you can say tan theta is equal to y by x. Y being 50 and x being 30 we got as 5 by 3. So theta is equal to tan inverse of 5 by 3 which gives us 59 degrees, approximately 59 degrees. So this will be, direction is given by this, direction is given by this, 59 degrees. Then the point of application of the force. To know the point of application, we talk about B. Talk about B, you can denote like this. Talk about B means, talk means the rotational effect of the force. This component X is passing through B, which cannot produce any torque, any rotation about B. Likewise, this 50 Newton also cannot produce any torque about B. So, Y and this 10 are the two forces that can produce a torque, rotational effect. Y can turn it clockwise with equal to Y times X, force times perpendicular distance. Clockwise torque, this 10 Newton can produce 10 times 5, because this length is 5 meters, 10 times 5. So that is the torque equation. Clockwise and anti-clockwise torques are balanced. So that means this will remain without rotation. So equilibrium means it should not move in linear direction, it should not move, it should not also not rotate. So rotation is prevented by this torque equation, where y is already we know is 50. So 50 cancel, implies x equal to 1 meters. X is equal to 1 meter. So we got all the three requirements. Magnitude is F equal to 58.3, F equal 58.3 newtons. Then direction is given by tan inverse of this, so 59 degrees. So if you apply this force, the single force about this point, which is x equal to 1 meter, single force at 1 meter from B, in this direction, this bar will remain in equilibrium without rotation, without moving to the right or left or down. It will remain in equilibrium. So that is the idea of this. Now if you want, you can also use the three forces when three forces are keeping a system in equilibrium or a body, the three forces must be concurrent, provided they are not parallel forces. So one force is this, another is this 50, the other force is this F. So if you draw the diagram, this 10 Newton this way, 50 Newton this way, they will meet at a point above, and this F will coincide with that direction, meeting at the same point. So I will draw that diagram after clearing this part. If you want that, if you are interested, you can try the problem in that way also. Now you can see the diagram on the vector diagram on the board. 50 Newton making this angle 37 degrees. So 50 Newton, you produce it up. 10 Newton also you produce it up. Then the resultant, the force that is going to balance these two forces is given by this line F. So if you are good in your geometry, you can try this with this triangle also. You can make this angle theta also. You will see that this angle theta will be equal to 59 degrees. So that also demonstrates that when three forces, non-parallel forces, keep a system in equilibrium, the three forces will be concurrent. This is the point P where the three forces are meeting. So that geometrically, if you want, you can work out. Those who are interested can try. Thank you.